Hello, everybody. Welcome. Today is going to be the last section of linear inequalities. We're going to tie everything together here. So it's going to be the optimization problems, the third part, linear programming, which we talked briefly about in some of the last videos. Solving optimization problems using linear programming. So we're going to create an algebraic model. That's what we've been doing. So we're going to identify the objective function that's going to be optimized, and the other quantities are going to depend on that. So it has nothing to do with the graph part. Like when you're graphing inequalities is at the very end. And again, we'll go through there. Define the variables at the very beginning when needed to. So give yourself an x and y for the variables so you know what you're referring to as you move through. Determine the restrictions on both variables. So that's the restrictions are the domain and range, right? Okay. They have to be considered. So, you know, your real numbers, your whole numbers, etc. And the constraints are the inequalities for the system. So when you're finding a solution, you're going to graph all the inequalities. You're going to determine that feasible region. That's the overlap of all the inequalities, and of course the restrictions as well. Evaluate the objective function using the coordinates of each vertex. So the vertex is whatever shape you get. So if you get a triangle that is going to be your shaded region, the vertex is all three corners of the triangle. Compare the results and choose which one is optimal conditions based on the question, right? If you're looking for a minimum or maximum, all right? So in example one, this is just a straightforward question. It says the following model represents an optimization problem. Determine the maximum solution. So the restrictions are the real numbers. For x and y, that means it doesn't have to be integer values. The constraints are the three inequalities. We're going to graph those, all right? And finally, the objective function will allow us to calculate which one we want to pick. So we're going to get to three. We'll probably get a triangle, and if we do, we'll pick the three vertices, right? So that's the corner of each on each triangle, and then we'll check to see which one has the value. So the first line, y less than or equal to 1. That's an easy one to graph. So we'll just graph that as is. Y less than or equal to 1. There's your graph there. Okay. With all the values less than that, we'll make that a little later. Okay. The second inequality we have here is 2y. So we got to divide everything by 2 there, right? So we want to rearrange that one. First one's fine. We don't got to do anything with that one. Second one, we'll divide everything by 2. So when we divide everything by 2, we'll end up with y greater than or equal to negative 3 halves x plus 2, when that's all rearranged. And remember, we didn't do anything with the first one, so I'll arrow that one off. We didn't do anything with the first one there, so it's just still greater than 1. Okay? And even the last ones, we're good to go with the last one as well. Don't have to touch that one. Oh, I forgot to divide by this one by 2 here, right? 2 divided by 2 is 1. You can make errors sometimes by mistake, but I caught it, so we're good to go. Oh, wrong inequality here. Again, not a big deal. Just make sure you put the right one, so you can easily do that, right? So that one is greater than or equal to. And remember, if it's 3, it's the same as 3 over 1. Okay? That'll just help with the rise and on. So there's the three inequalities. All right? I've already graphed the first one, y less than or equal to 1. Graph the second one here, y greater than or equal to negative 3 halves x plus 1. Y greater than or equal to, and was it negative? Yes, it was. Negative 3 halves x plus 1. And we will lighten that up a bit. Okay. Remember, it's above, so it's here. This one's below. And the final graph we had was y greater than or equal to 3x minus 8. So y greater than or equal to 3x minus 8. And make that a little lighter as well. And you'll see that the overlap is among these three triangles there, right? Or the three corners of the triangle there. There they are. That is the overlap of the three inequalities. So remember, the shaded, or the feasible region, or the shaded region, the overlap makes this triangle here. So those are the 3 points that we're going to see which is the maximum, which was the min. Where we look for the max. So we'll check the points, check each of the points here. The first one we'll check is 0 and 1. Plug them in. So put 0 in for x, 1 in for y. So that's equal to 0 plus 3. That's equal to 3. And we'll do this again. And so I'm just going to see all this for a minute. And at this point, we're going to use 3 and 1. So this is 3, which makes negative 12, which makes negative 9. And then the last point is 2 and negative 2. 2, negative 2. So plug those in. 2, negative 2 gives us negative 8, minus 6, which is negative 14. So, this point here, so that means that 0, 1 is the maximum solution, right? If I asked for the minimum solution, that would have been 2 and negative 2, okay? So the answer is 0, 1 is the maximum solution because it yielded the largest value, d equal to 3. Okay? And that's it. As for the min, it would have been here. And the other one doesn't. Good, thanks for the question. So next, we have a word problem. So I think we'll finish the video there, and in the next video we'll look at example 2, which is the last question for our chapter. Thanks everybody for watching. We'll talk again soon.